we're going to talk about existence and uniqueness of solutions to a differential equation. Before we do so, let's review what we discussed last time, some properties of Euler's method. Consider the following initial value problem. dy dt is f of t comma y, where y of t0 equals y naught. We know that in general it is difficult to find an exact solution, so we'll discuss how to find an approximate solution. The idea is as follows. Say that we have a solution y of t to this initial value problem. If we choose some time value t1, which is near the initial time value t0, we'll explain how to find a value y sub 1 that is near the value y evaluated at t sub 1. The idea is to consider a secant line going through the 2 points t0, y0 and t1, y1. We'd like for the slope of the secant line to be equal to the slope of the tangent line. But because the slope of the tangent line, dy dt, is just f of t comma y, then we find that the slope of the secant line, that is y sub 1 minus y sub 0, divided by t sub 1 minus t sub 0, is equal to f evaluated at t0 comma y0. So solving for y sub 1 gives an expression y sub 1 equals y sub 0 plus f of t0 y0 times the difference t1 minus t0. This will be approximately equal to the value y evaluated at t sub 1. We're going to use this expression here to proceed in a recursive fashion. So here's the idea. First, fix a step size h, which we'll also denote as delta sub t. The idea is that this step size should be a very small number, perhaps h equals 0.1. Recursively now, we'll perform the following steps. Number 1, compute the slope f evaluated at t sub k, y sub k. Second, update this time and consider t sub k plus 1, which is t sub k plus the step size h. Third, compute the new value y sub k plus 1 equals y sub k plus f evaluated at t sub k times y sub k times the step size h. And finally, we'll return back to the first step by replacing k with k plus 1. The plot of these points, t0, y0, t1, y1, and so forth, will be an approximate plot of the graph of the actual solution, y of t. This technique of finding an approximate solution is known as Euler's method. Today, we'd like to discuss the existence and uniqueness of solutions to a differential equation. So here's our motivating question. Consider an initial value problem, just like before. dy dt equals f of ty, where y evaluated at t0 is equal to y0. Before we look for methods on how to find a solution y of t, how do we even know that a solution exists? Well, this is the content of the following theorem, simply known as the Existence and Uniqueness Theorem. Say that we have a rectangle, capital R, which is the set of points t comma y, where the time t is between two numbers a and b, and the value y is between two numbers c and d. Let's assume that we have three conditions. First, f of ty is a continuous function on this region. Second, the partial of f with respect to y should also be continuous on this region. And third, the initial value, namely the point t0, y0, must be in this region. If all three of these are true, then there exists an interval involving the time t between t0 minus epsilon and t0 plus epsilon, such that the initial value problem has a unique solution defined for all time t in this interval. Here, we'll give a graphical interpretation of what's happening. Let's consider the following initial value problem, which comes from looking at an object falling under gravity, but under the influence of air resistance. In this case, we've plotted out the slope field. These would be the arrows that you see here on your screen. Here, on one axis, we have time, and on the other axis, we have velocity. We can see that the box here is our region R. In this case, we see that the function f of t comma v, that is minus g minus gamma over m times v, is a function that is continuous for everything that you see on your screen. In fact, even if we were to take the partial of this with respect to v, it's also continuous for every point here that you see on your screen. So the point here is that we can look at every point, every arrow that you see on your screen, and we can think of this as our region R. So quite literally, the region R is just the square that you see here on your screen. Now, let's give a proof of this result that we're calling the existence and uniqueness theorem. The idea of this proof will be to use the following identity. First, let's say for the moment that y of t is indeed a solution to the initial value problem. Then this means that y prime of t is f evaluated at t, comma, y of t. Let's take this expression and simply integrate both sides. Then we'll see that y of t equals the integral from t0 to t, f evaluated at tau, comma, y of tau d tau, plus some constant y evaluated at t0. We're going to use this expression to define a sequence of functions y sub 0 of t, y sub 1 of t, and so forth as follows. First, define y sub 0 of t as just the constant function that takes on the constant value y sub 0. Next, let's define y sub k plus 1 of t as the integral from t0 to t of the function f evaluated at tau, y sub k of tau d tau, plus the constant y sub 0. Notice that if we differentiate y sub k plus 1, then by using the fundamental theorem of calculus, we see that this is equal to f evaluated at t, comma, y sub k of t. Similarly, if we plug in t equals t0, then we see that y sub k plus 1 evaluated at t0 is equal to y0. So it almost looks like these functions y sub k are the solution that we're looking for. So let's consider the limit as k increases without bound. We're going to call this a function y sub t. We notice that it has two properties. First, the derivative y prime of t is equal to f evaluated at t, comma, y of t. Second, we see that y evaluated at t0 is just our initial value y sub 0. So this means that our function y, this limit as k increases without bound, is indeed the solution that we're looking for. This technique of approximating the solution we're looking for as a sequence of approximate solutions, these y sub k of t, is what's known as Picard's method. We'll discuss a little bit more about this in a moment. First, let's give an example illustrating some of the ideas we just worked out. We claim that the unique solution to the following initial value problem, dy dt equals 2t times 1 plus y, where y of 0 equals to 0, is the function y of t equals e to the t squared minus 1. We're going to give two different methods on how to solve this differential equation. First, we notice that this is an exact equation, so we notice that this is a separable equation, so we can use the methods that we've discussed before. If we have dy dt equals 2t times 1 plus y, we'll bring all of the y terms to one side and all of the t terms to the other side. Once we integrate, we find that y plus 1 equals a constant c1 times e to the t squared. By plugging in t is equal to 0 and realizing that y of 0 equals 0, we find that c sub 1 equals 1, and therefore y of t equals e to the t squared minus 1, as we originally claimed. Now let's introduce a second method using the idea that we just illustrated, that is the idea of Picard iterates. We'll form a sequence of approximate solutions. Let's define the sequence iteratively as follows. Y sub k plus 1 equals the integral from t0 to t f of tau, comma, y sub k of tau d tau plus a constant y sub 0. In this case, f of t comma y is equal to 2t times 1 plus y, and y of 0 equals 0. We can work out the first few iterates. For example, y sub 0 of t is just the constant 0. Remember that the first function, y sub 0 of t, is always the constant function that takes on the value y sub 0. Next, for y sub 1, we'd like to integrate from 0 to t twice tau times 1 plus y sub 0 of tau. In this case, y sub 0 of tau is just the constant function 0. So we're integrating twice tau d tau as tau goes from 0 to t. This is equal to t squared. For the next iterate, y sub 2 of t, we'd like to integrate from 0 to t twice tau, 1 plus y sub 1 of tau. In this case, y sub 1 of tau is simply tau squared. And once we work out this integral, we see this is equal to t squared plus t to the 4 divided by 2. One can continue in this fashion to find that there actually is a pattern here. Y sub k of t is equal to t squared plus t to the 4th over 2 factorial plus t to the 6th over 3 factorial, and so forth. Now, let's take the limit as k increases without bound. This was how Picard's method worked. Once we worked out the Picard iterates, we can now take the limit as k increases without bound. We find y sub t is equal to a sum, n goes from 1 to infinity, t to the 2n over n factorial. Now let's just recall the power series expression for e to the x. If we substitute in x equals t squared, then this power series is simply equal to e to the t squared minus 1, which is exactly what we found on the previous slide. We'd like to point out that these functions, y sub k, do indeed give a very good approximation to the exact solution y of t. Here's another example. Let's consider the following initial value problem. We'd like to know what is the largest region R such that there exists a unique solution. Well, first, let's just go about solving this initial value problem. Just like before, we see that this is a separable equation, so we can simply go through the methods that we're used to. What we find is that y of t equals 1 plus or minus the square root of an interesting function that you see here on your screen. We can determine the constant by using the fact that y of 0 equals minus 1. This forces the constant c is equal to 3, and it also forces us to choose the negative square root that you see on your screen. Therefore, the unique solution to the initial value problem is y of t equals 1 minus the square root of t plus 2 times t squared plus 2. Now let's go ahead and plot this solution. On your screen, you actually see two plots. The blue upper half is what the plot would look like if we had 1 plus the square root. The gold lower half is what happens when we have 1 minus the square root. The gold lower half is indeed the function y of t. Now, the square root is only defined when what's inside of the square root is a non-negative number. Since t squared plus 2 is always positive, we see that t plus 2 must be greater than or equal to 0. So this means that t is greater than or equal to negative 2. If you stare here at the box that's on the screen, we see that that box is indeed the region R. That is, t must be greater than negative 2, and therefore we see that y has to be less than 1. The reason it has to be less than 1, of course, is that y of t is equal to 1 minus the square root. So the box that you see on your screen, the box that encloses the gold part of the graph, actually must be the region R. Thanks very much for watching.